Hello. Hello. Teja Garu.
Yes, sir. Good afternoon, sir.
Good afternoon, madam. Have you taken lunch?
Yes, sir.
Okay. I
You,
think
sir?
I also took. And our friend, Mr. Bhanu Prasad, the most sincere student, or rather one of the most sincere students, he must be taking lunch.
Okay, sir.
Who is this? BV? BV means who it is? What is the full name? BV means? May I know? BV means? Okay. Actually, yesterday I was first I defined a complete orthonormal set in an inner product space. A complete orthonormal set in an inner product space. Okay. And then I defined, I showed that every inner product, every non-trivial inner product has got a complete orthonormal set in that. Okay, there is another theorem on complete orthonormal sets. It is very easy to prove. It is a proposition 12.5.3. 12.5.3. This I forgot to prove, proposition. This I forgot to prove. Today I will do that. Okay. Then without doing this, I went for Gram-Schmidt orthonormalization process. Okay. So because I have already started this Gram-Schmidt orthonormalization process, I will complete this and then I will come back to this proposition. And then we'll move to the next of this orthonormalization. Okay. That's what I want to do today. Right. So, yeah. Let us mention, I will do this Gram-Schmidt orthonormalization process fully today. Yesterday I started, I could not complete it. Okay, first let me state that. Let X be an inner product space and X1 up to Xn contained in X be linearly independent. Linearly independent set. For some natural number n. Okay, for some natural number n, any set of natural numbers. Okay, then
good afternoon.
Yeah, good afternoon, Bhanu Prasad ji. Then there exists orthonormal vectors, orthonormal vectors y1, y2 up to yn, right? In X such that the linear span of this is equal to the linear span of this, such that linear span of x1 up to xn is equal to linear span of y1 up to yn. Okay, right? X is an inner product space. Hope I am audible and visible, right? Right? Are you able to see the screen?
Yes, sir. Yes, sir.
I'm also audible, right?
Yes, sir.
Okay, okay. Now, let X be any inner product space, and you take, say you have n linearly independent vectors, x1, x2 up to xn in X. Okay, these are linearly independent vectors. I'm assuming this set is linearly independent. Let set consisting of x1 up to xn contained in X be linearly independent. A set is said to be linearly independent if the elements of it are linearly independent. Okay. set for some natural number n, this n is some natural number, then there exists orthonormal vectors y1, y2 up to yn in X such that the linear span of these n independent vectors, linearly independent vectors, is equal to the linear span of these n orthonormal vectors. These are orthonormal vectors. Okay. What is the difference between xi's and yi's? Yi's are orthonormal vectors. What do we mean by orthonormality? These are orthogonal, and each of them is of size 1. Okay. If you have a certain number of vectors which are orthogonal pairwise, and if the size of each of them is 1, they are unit vectors. Orthogonal means yi intersection yi, the scalar product of yi and yj is empty, is 0. If yi yj for I not equal to j, if this inner product is 0, okay, then we say these two vectors are orthogonal. That's what we mean by orthogonality. If in addition to the orthogonality, if we also have this normalization, this is called normalization. Means if each of them is a unit vector, right, then we say these are orthonormal vector. Okay. So whenever you have n linearly independent vectors in an inner product space, you can construct the same number of orthonormal vectors such that the linear span of these linearly independent vectors is also equal to the linear span of these orthonormal vectors. In fact, we proved in one of the propositions before that if an inner product space, if you have orthonormal vectors, then they will be linearly independent. Even if they are not orthonormal, if orthogonality is enough. If you have n orthogonal vectors in an inner product space, you can show that they are linearly independent because of this property. And that yi, yi, the inner product for the same vector is non-zero. Is what? Is norm yi square, and this is positive. Why? This cannot be zero vector. Why cannot be zero vector? Okay. Right. Yeah. Then it cannot be right. Then zero vector. Then it will not be linearly independent. Okay. Y is non-zero. So that's why norm of y square. Norm y square. This square must come out. This square must come out. Norm y square is positive. Okay. Therefore, that gives norm y is positive. Therefore, y will be non-zero. Okay. Right. It is non-zero vector. Okay. So if you use these two conditions, you can show that any set of n orthogonal vectors is linearly independent. That's what we did before. We took a linear combination and we applied this scalar product operator on that. Okay? And we used these two properties to obtain that the linear combination sigma lambda I by I. Okay, so we could obtain that lambda I equal to 0. Okay, right? This we obtain for each I. And this we could obtain. Okay. Now, in this theorem, if you are given n linearly independent vectors, we'll be constructing n vectors y1, y2 up to yn, such that these are orthonormal, and that the linear span of this is equal to the linear span of this. Okay. And what does this mean? What does this mean? It means that see, as I was saying, if you have R3, in R3, the standard vectors are 0, 1, 0, 0. This is I bar, and 0, 1, 0. This is right. This is the endpoint of J bar, and 0, 0, 1 is the endpoint of K bar. I bar, J bar, K bar form an orthonormal set of vectors. I bar dot J bar equal to 0. right? If you go for this scalar product, I bar dot j bar is 0, j bar dot k bar is 0, I bar dot k bar is 0. Okay, and these are unit vectors. Okay, and you can take a different basis for I R3, right? 1 0 0, and then 0 1 1, and then 0 1 3. I think if you take like this, right? This is not scalar times of this. This is not scalar, right? These are linearly independent. These are linearly independent. These are linearly independent. You can see that these form linearly independent vectors in this. Okay. So, and you can also show that the linear span of these vectors is equal to the linear span of these vectors. Okay. Right. So in R3, we can visualize this. Okay. So whenever you have an inner product of finite dimension, if the inner product has if it has a basis of finite size, then what this orthonormalization process says is that in fact you can replace this by a set of orthonormal vectors of the same size, which can work as basis. Okay, here if in case your X is finite dimensional, you can find a basis. If the size of X is n, you can find a basis for X. Okay, right? Means this spans the whole of X. Okay, so yeah, in that case, in fact, you can construct orthonormal vectors of by the same number n, and that the span of these orthonormal vectors is equal to the span of these vectors, the linear spans. I mean, so it means that the Gram-Schmidt orthonormalization process enables us to replace a finite dimensional inner product space with a basis of orthonormal vectors. Okay, right? So that is the strength of this. Here, by orthonormality, we mean the angle between them is right angle. Okay, but here we don't know about the angle between these pairs of vectors. Okay, that is the difference between orthonormal vectors and ordinary vectors. Okay, let us see how we can do this. Right? There are many examples in your book. There are some 3-4 examples worked out in your book. Okay, if you can understand the theory, you can work out the examples. Okay? So we proceed like this. Yeah. Proof. So let us start with X1. Right? We have. Let us take this to be linearly independent in X. Let X1 up to Xn be linearly independent in an inner product space, capital X. Okay. Let us start with an inner product space capital X, and in that, let us take a linear independent set for some natural number, for some natural number n. Okay. Now we'll construct these orthogonal vectors. Okay. We start like this. We prove we may call this theorem. You may call this process a theorem. You may call this a theorem. Okay. We will prove this theorem by induction. We'll prove the theorem by mathematical induction. Okay. Induction on n. Induction on n. Okay. First, we'll prove the theorem for n equal to 1, and then we assume it for n up to n minus 1, and we'll prove it for n. Okay, that's how you apply mathematical induction. So we'll prove it. We'll prove the theorem by induction on n. So okay, let n be 1. If n is 1, you have consider x1. You are right. You have single. You are assuming n equal to 1. So this set becomes a single term. It consists of x1 alone because n is 1. Okay, and consider this. And this is x1 is linearly independent. Means what? Your x1 is not equal to 0. Okay, a linearly independent vector cannot be 0 vector, right? Otherwise, what happens? You can write if your x1 is 0. If your x1 is 0 vector, you can write 0 vector as 2 times 0. Okay, and this is 0. If you multiply 0 by any scalar, the scalar product is 0. Okay, but the scalar is non-zero. Okay, so this is a linear combination for which the linear combination is 0 vector, but the scalar is non-zero. Therefore, your 0 vector will not be linearly independent. But we assume that x1 is linearly independent. Therefore, your x1 cannot be a 0 vector. If your x1 is 0 vector, you have this argument. Okay, your theta turns out to be linearly dependent. This becomes linearly dependent, but x1 has to be linearly independent. That's why you have this. Okay, because of this reason. Now we'll construct a y1. Define y1 is equal to x1 by norm x1. Once this linearly independentness of x1 gives you that your x1 is non-zero, your norm x1 will be a positive number. This implies norm x1 is non-zero. In fact, it is a positive number because x1 is non-zero vector. Its norm has to be a positive number. It cannot be 0. Okay, norm is always greater than or equal to 0 because this is non-zero vector. Your x1 has to be in norm has to be a positive number. Okay, so that can be in denominator. This is a positive number. It can be in denominator. So this is a scalar times scalar 1 by norm x1 minus this vector. So this is well defined. Okay, consider this. Okay, right. Yeah, and yeah. If you consider y1 alone, x1 by norm x1, the set consisting of y1 alone. If you consider the set consisting of y1 alone, this singleton, then right, this is replaced by this one, and a singleton, right? In this set, you have only one element. We assume that it is linear, it is orthogonal, right? Orthogonal, right? If you have more than one element, then if this set has two elements, a minimum two elements, then to check whether this set is orthogonal, you have to consider their scalar product. Check whether this is 0. But you don't have the second vector. You don't have the second distinct vector. So we assume that this is, by definition, we assume that this singleton is orthogonal. Okay, and then we look at its norm. What is the norm of this? Norm y1 is equal to norm of x1 by norm x1. Right? Now for y1, I am replacing. I am substituting this x1 by norm x1. This is this norm. This is a scalar. This comes out. This is 1 by norm x1 into norm of this. Okay, and norm x1 is a positive number. Positive number by the same positive number is 1. Therefore, y1 has norm 1. We say we have normalized y1. This is called normalization of y1. Means the length of this vector y1 has been 1. Means y1 is a unit vector. Okay, so and right. So yeah. So we have this set becomes orthonormal. Okay. Therefore y1 is equal to x1 by norm x1 is orthonormal because it is orthogonal and also its size is 1. Therefore, this set becomes orthonormal. Okay, and we'll show that the linear span of singleton x1 is linear span of this vector y1. Okay, how? See now. Yeah. This means what? From here you get that x1 is scalar. This scalar times y1. Okay, y1 equal to x1 by norm x1. This gives that x1 is equal to scalar x1 times y1. You take this to the other side. This is a scalar either right? Yeah, this is a positive number. So you take this to the other side. You have this. So this x1 is a scalar times of y1. So if you take a linear combination of this, it will be a linear combination of this. This implies a scalar c times x1 is equal to scalar t times norm x1 into y1. Okay, for c belonging to the field. Okay, I am taking a scalar f c from field, right? for which X is an inner product. Okay. Now, see, I'm multiplying X1 by this scalar. So multiply this by C. So this is scalar, this is scalar. These two can be clubbed by vector space definition into Y1. Okay. These two can be clubbed into this vector. So this scalar multiple of X1 is also a scalar multiple of Y1. Okay. This implies that the linear span of X1 is contained in the linear span of Y1. Okay. So, right, because of this, if you what is linear span of X1? You have to multiply X1 by scalar C. Okay. So this is right. So this can be, so this scalar multiple is also a scalar multiple of this. So you can write like this. How about the converse? If you take a scalar multiple of this, can it be written as a scalar multiple of X1? Let us see. So let or consider conversely consider a scalar d times y1 for d belonging to the scalar field. Okay, you take a scalar multiple, you take an element from here. What is it? What is its form? It is the singleton. So you have to multiply this by a scalar. Okay, it is of the form dy1. What is y1? This is dy1. And what is y1? Y1 is x1 by norm x1. x1 by norm x1. Okay, and this also is scalar. Norm x1 is scalar. You can club that with d. So this is d by norm x1 into x1. Okay. In this set, vectors are of the form scalar times of y1. They are of the form d into y1. Okay, for some scalar d. So dy1 is equal to, for d, what is y1? x1 by norm x1. So and this is scalar. This can be clubbed with this d. So it is d by norm x1 into x1. So this scalar multiple, and this also is a scalar, is also a scalar multiple of x1. So this implies that linear span of y1 is contained in linear span of x1. Okay. So a scalar times of y1 is also a scalar times of x1. So this is contained in this, right? So reverse inclusion also works. Therefore, this is equal to this. Okay. Linear span of this is equal to linear span of this because this is subset of this. Okay. Therefore, linear span of singleton x1 is equal to linear span of singleton y1. Okay. So we showed that singleton y1 is orthonormal and also that the linear span of x1 is equal to linear span of y1. Means the theorem is true. Thus the theorem is true for n equal to 1. Okay. Now we'll show how we can construct another orthonormal vector with the help of y1. Okay. And then we'll go for the induction hypothesis. Right. Now let us construct a y2 such that y2 comma y1 they are orthogonal and that norm y2 is also 1. Okay. Let us construct an orthonormal vector y2 such that the inner product, its inner product with y1 is 0 and that it is 1 in size. Okay. So to do this, we define like this. Define z2 is equal to x2 minus inner product x comma y1, x1 comma y1 into y1. Okay. If you do like this, right? See, y1 is a vector and this is a scalar. x1 and y1, these are scalars. See, we started with x1. We defined a y1. Out of x1, we constructed a y1. Okay. Now using this y1 and x1 and also x2, we are defining a Z2. Using this, we'll define y2. Okay, that is the technique. And in fact, we'll construct Z2 such that Z2 and y1 are orthogonal. Okay, to do that, see, this is a scalar. Scalar times vector is a vector. This is a vector. So this difference is a vector. So Z2 is a vector. And the technique is that we want Z2 with y1 has inner product 0. We want y2 replaced by Z2 gives us the inner product of Z2 comma y1 is 0. So we will construct in such a way that Z2 in such a way that its inner product with y1 is equal to 0. So you calculate the inner product of this with y1. So x2 comma y1 comes here minus x1 into y1 into this is y1 comes here, right? We'll take the inner product of this with y1. In fact, here I should go for x2. I think x2. Yeah, I have to go. Right? Because here if I take the right, if I take the inner product with y1, here comes right. I will take the inner product of this with y1. Okay. Then what happens? Then you get x2 comma y1 here minus I want y1 inner product y1 becomes norm y1 square. Y1 is unit vector, norm y1 square will be 1. Here I should get right the inner product of x2 with y1 has been x2 y1, inner product x2 comma y1, and therefore here I expect x2 comma y1. So here I must take x2. Okay. So yeah, let me make this change. Let me take here x2. So if I define like this, yeah, define Z2 to be this and consider Z2. Now, what is inner product of Z2 and y1? This is equal to you take the inner product of this with y1 on both sides. So you will have x2 minus x2 comma y1, right? I am taking the inner product of this with y1 on both sides. So it is inner product Z2 comma y1 is equal to inner product for Z2. You have this x2 minus inner product x2 y1 comma y1 comes. Okay. In place of Z2, I have taken this one x2 minus inner product x2 comma y1 comma right. This all has come comma this y1 is coming. Now expand this. Right? This is linear in the first variable. So this becomes, this inner product is x2 comma y1. Then minus comes. Then this is inner product x2 comma y1. Right? y1 into y1 comma y1. Agree? So this minus this may be taken out. Then this inner product comes x2 y1 into y1 comma y1 comes. Now this is equal to how much? x2 y1 minus this is a scalar. It can be taken out. The inner product is linear in the first coordinate, this coordinate. So this is scalar. This can be taken out. So you have x2 comma y1 inner product. What remains is vector y1. Okay. This scalar comes as it is minus this is a scalar and inner product is linear in the coordinate 1. So this scalar comes out as it is. So the into minus this scalar x2 comma y1 into inner product y1 comma y1. Okay. This is norm y1 square. Norm y1 is 1. Okay. Therefore, this becomes x2 comma y1 minus this is x2 comma y1 and this is norm y1 square, and norm y1 square is 1. So right, this is x2 comma y1 minus x2 comma y1 into 1. This is 0. Okay. This is 1. So 1 into this itself x2 inner product x2 minus x2 y1 minus inner product x2 y1. It is equal to 0. Okay. It means Z2 is orthogonal to y1. Okay. Right. So out of this Z2, we define a norm unit vector. out of this Z2, we define a unit vector. How? Yeah. We also have to observe that this Z2 is non-zero. If this is 0, what happens? If Z2 is 0, your x2 will be, this goes to the other side. If you make it equal to 0, this goes to the other side. So your x2 will be this scalar times y1. So your x2 will be a scalar times y1, and y1 is a scalar times x1. So your x2 will be a scalar times x1. Means your x2, x1 are linearly dependent. That is contradiction. We took x1, x2 to be linearly independent. These are linearly independent. So okay. So because of that reason, the linear independence of x2, x1 gives you that your Z2 is non-zero. Okay, let us put it in words. If Z2 is equal to inner product, it is right. It is here what? X2 minus inner product x2 comma y1. If this is equal to 0, right? Your Z2 is this. X2 minus inner product x2 comma y1. X2 minus x2 y1. Yeah. If this is equal to 0 vector, this is a vector, this is a vector. So if this is 0 vector, then x2 is equal to how much? You take this to the other side. Okay. It is x2 comma y1. Scalar this times y1. Okay. And for y1, you can write what this is. Okay. X2 y1 in scalar in y1 is x1 by norm x1. Okay. Y1 is x1 by norm x1. That's how we define y1. So this is a scalar, this is a scalar. So this is a scalar multiple of x1. Okay. Means this implies that x1 comma x2 are linearly dependent. Okay. And this is a contradiction. This is a contradiction because your x1, x2 are linearly independent. Okay. So implies that yes.
This is the step x2 comma y1 multiplied by x1 by norm x1 or norm y1, sir.
Which one? This one? x1 by norm x1.
Norm x1.
x1 by norm x1. Yeah. x1 by norm x1. This is y1. y1 is x1 by norm x1. Okay?
Yes, sir.
y1 is x1 by norm x1. So this is scalar x2 comma y1 by scalar norm x1 into x1. Okay? This is scalar product. Okay? So this vector is scalar times of x1 vector. So you will get x1, x2 are linearly dependent. It is a contradiction to the fact that your x1, x2 are linearly independent. Okay? That is why this cannot be 0 vector. Okay? Once it is non-zero, you divide this vector by its size. So define y2 equal to z2 by norm z2. Okay? This is your y2. What is z2? It is x2 minus x2 y1 into y1 by norm x2 minus x2 y1 into y1. Okay? Right? You define a unit vector out of this. You divide this by its size. You get a unit vector. Okay? And because here what you have done, you have shown that y1 z2 are orthogonal. Okay? Because of this, and your y2 is a scalar times of z2. Okay? If you give a number for this, 1, here y1 z2 are orthogonal. Right? One implies that z2 comma y1 equal to 0. Y1 z2 are orthogonal. Now here y2 is a scalar times 1 by norm z2 into z2, and z2 y1 are orthogonal. So y2 y1 will be orthogonal. Okay, so you have y2 y1. If you take the inner product of this is y2 is what? z2 by norm z2 comma y1. Okay, right? This scalar can be taken out as it is linear in the first coordinate into z2 comma y1. Okay, you consider the inner product of y2 and y1. Okay, now for y2 it is z2 by norm z2, And this is scalar, you take it out, 1 by norm Z2 into inner product Z2 comma Y1. And this is shown to be Z. So this is 1 by norm Z2 into 0. And this is 0. Okay. So Y1, Y2 will also be orthogonal. And Y2 is of one unit vector. Y1 is also one unit vector. Y1 is also one unit vector. Therefore, Y1, Y2 will be orthonormal vectors. Okay. Right. Therefore, Y1 comma Y2 is orthonormal. Okay. And then orthonormal. Okay. Now, this is what we have done is that if we know 1 by 1, out of that, if we know one by 1, orthonormal vector Y1, out of that we can construct another Y2 which is orthonormal to Y1. That's what we have exhibited. Okay. Now we proved the theorem for n equal to 1. We will assume the theorem for n minus 1 and prove it for n. Okay. Let the theorem be true for n minus 1. Okay. For some natural number n. Okay. Let us assume that the theorem is true for n minus 1 for some natural number. We will prove the theorem for n. So by induction argument, it follows that the theorem is true for all natural numbers n. Okay. Right. So this means what? What does this mean? This means that, of course, here we did not show that. Even if you did not show, it's okay. That it will be assumed. We proved the theorem for n equal to 1, and we are assuming the theorem for n minus 1. So that gives us that linear span, right? Therefore, there exists orthonormal vectors Z1, Y1. This is Y1, Y2 up to Yn minus 1, right? Such that the linear span of x1 up to xn minus 1 is equal to the linear span of y1 up to yn minus 1. Okay. Well, we assume the theorem for n minus 1. What does the theorem say? It says that if you have n linearly independent vectors, you have n orthonormal vectors, so that the linear spans of them are identical. Okay, and we are assuming the theorem for n minus 1. So you have to replace n by n minus 1. So this is true. This is true. N replaced by n minus 1 is true by assumption. Now we'll prove the theorem for n. We'll have n vectors here and n vectors here, and we'll try to obtain the equality between linear spans. Okay, and we also construct a yn which is orthonormal with all these n vectors. Okay, and to construct a yn which is orthonormal to each these n minus 1 vectors, we follow this technique. From y1 we constructed a y2. From y1 we constructed a y2. Right, this is y1, and we constructed a y2. Yeah, if you know a orthonormal vector y1, this gave us y2. This led us to y2. Okay, Z2. First we formed Z2. Out of that we normalize that to get y2. Okay, so this is the main idea. From here to here, constructing Z2 is the crux of this theorem. Okay, so we use this concept to construct yn. Okay, see, define yn is equal to xn minus inner. It is summation. Or you can expand. It is xn comma y1 into y1 minus xn comma y2 inner product into y2 minus and so on, inner product minus inner product xn comma yn minus 1 into yn minus 1. Okay, you consider this vector. Previously, what we did, we defined a Z2 to be x2, right? This suffix is 2. Take x2 minus, take same xn here. And then you reduce the suffix by 1, y1, and take the same y suffix here. Okay. So do it for Zn. So in fact, you call this Zn. Call this Zn. Define Zn. Okay. So start with xn and take the inner product of xn with y1, and then take y1 here. Then take the inner product of xn with y2 and take y2 outside and continue this. And take the inner product of xn with yn minus 1, take yn out and minus 1 outside. What does this give us? If we do like this, okay, you see, you take the inner product of Zn with yk. So for 1 less than k less than or equal to n minus 1. Okay, so assume your k is a number between 1 and n minus 1, a natural number between 1 and n minus 1. And you consider the inner product of Zn with yk, right? I want to show that Zn is orthogonal with y1, y2 up to yn minus 1. That is my objective. So take yk, you call yk for k lying between 1 and n minus 1. Take the inner product of this with yk. So this becomes how much? It is xn. If you are taking the inner product of this with yk, so it is inner product xn minus inner product xn comma y1 minus inner product xn comma y2 into y2 minus and so on minus inner product xn comma yn minus 1 into yn minus 1 comma yk. Okay, you take for Zn, I have written all this. And then comma, this is comma yk you take. Right now, what is the help of this? If your k is 1, so xn comma y1 minus here y1, the inner product of y1 with y1 will be 1. It is down y1 square, it is 1. So and this and xn comma y1, the two cancel out. And the other ones, if you take k equal to 1, y2 is orthogonal to y1. So y2 inner product y1 will be 0. Similarly, y2, right? y1 will be orthogonal with yn minus 1. So inner product of yn minus 1 with y1 will be 0. Okay, and if in case your k is 2, the inner product of y2 and yk will be 1. And this into 1 comes, and you are taking the inner product of this with y2. So this gives an inner product xn comma y2, and from here you get a inner product xn comma y2, and it is with minus. So their sum will be 0, and inner product of y1 with y2 will be 0. So and everything else also will be 0. Inner product of y2 with yn minus 1 will be 0. So that is the use of these vectors. This vector contributes for norm y1 square, and this vector contributes for norm y2 square. This contributes for norm y1 square when you take k equal to 1. This contributes for norm y2 square when you take k equal to 2. This contributes for norm yn minus 1 square for k equal to n minus 1. The other vectors, these subvectors, their norms will be zeros because of orthogonality. Okay, so that's how this will be 0, right? See, this is what I will write. I will write this as an expression. This is xn minus sigma xn comma yi inner product yi I equal to 1 to n minus 1 comma yk. Okay, I have abbreviated this, right? So it is xn, and this can be written as xn comma, you call this yj. You bring a variable here. It is yj, yi into yi, right? And I is varying from 1 to up to n minus 1. Okay, comma this is yk. So this becomes how much? This is so inner product Zn with yk is equal to this. You may take out because inner product is linear in the first coordinate. This can be taken out. This right. So this can be written as xn comma yk minus sigma xn comma yk. Right, this comes out sigma I equal to 1 to n minus 1, sigma I equal to 1 to n minus 1. This is Yeah, and you have to take yi comma yk. This can be taken out, okay? Because it is linear in the first coordinate, so sigmas can be taken out, right? So yi comma yk comes, yi comma, right? Comma yi comma yk, yi comma yk. Okay, and again, this is scalar. We can take out because it is linear in the first coordinate. This is sigma xn comma yk minus. When is this non-zero? This r minus sigma. This is xn comma yk inner product yi comma yk. Okay, I have taken this scalar outside the inner product. This is I equal to 1 to n minus 1. Okay, and I and k, and I is the variable for fixed k value. You fix k value, fix k between 1 and n, you fix k between 1 and n minus 1. For that fixed value, you let I vary. So I is varying. So for one I value, I takes k. So for that I value, when I is k, this is norm by k square. For all other i's which are different from k, this is 0. Okay, so this is sigma xn comma yk minus when you were right. In fact, take this out. I think this is xn comma yi. I forgot this I. You see, xn comma yi. Okay. So xn comma yi, this should be yi. I'm sorry. This is yi. Okay. So yi. Agree? This is xn comma yi. y1, y2, y2. So these two are same. So it is xn comma yi. So it is xn comma yi, xn comma yi. Okay. And this comes out. Now I is varying. So when I is k, you get inner product xn minus yk into norm yk square into norm yk square. So I is varying. When I is k, this term will be xn yk into yk. The other terms, when I is not equal to k, this is 0, right? Since yi comma yk is 0 for I not equal to k. Okay, this I used. If your I differs from k, this will vanish. So you don't need to write the other n minus 2 terms. Okay. Now this is norm yk square is 1. So these two are same. So this is norm xn minus yk minus xn. It is not norm. It is inner product minus xn comma yk. So into 1. So this is 0. Okay. Since norm yk square is 1. Okay. This is norm yk square. So Zn and yk have been orthogonal for all k's between 1 and n minus 1. Okay, k is between 1 and n minus 1. For this case, we showed that Zn is orthogonal with yk. Okay, now out of this Zn, we'll construct a yn. Define yn equal to Zn by norm Zn. Again, you can observe that your Zn is non-zero. Why? If your Zn is 0, your xn will be in terms of y1, y2 up to yn minus 1. These can be taken to the other side. If your Zn is 0, your xn can be written as y1 can be written in terms as a linear combination of y1, y2 up to yn minus 1. But linear span of y1, y2 up to yn minus 1 is linear span of x1, x2, xn minus 1. Therefore, your xn becomes a linear span of x1, x2 up to xn minus 1. This means your x1, x2 up to xn will be linearly dependent. That is contradiction for the hypothesis. Therefore, your Zn cannot be 0 vector. Okay, so you have to mention that. Let this be. Zn is not equal to 0. Zn is not equal to 0 vector because Zn equal to 0 implies xn is a member of linear span of x1 up to xn. Okay, Zn is equal to 0 gives you Zn equal to 0 gives you that your xn is a linear span of y1 up to yn minus 1, which is equal to the linear span of x1, x2 up to xn minus 1. So So your Zn will be, your Xn will be in the linear span of X, X1 up to Xn minus 1. Okay. This means X1, X2 up to Xn minus 1, Xn, these are linearly independent. This implies X1 up to Xn are linearly dependent. Okay, this is a contradiction. This is a contradiction. Okay, therefore your Zn cannot be zero vector. So norm Zn is a positive number. You can divide Zn with a positive number, and the size of this is 1 because Zn is orthogonal with y case. Yn also will be orthogonal with y case for all these cases. Okay. Further. Yn inner product yk will be 0 for k equal to 1 up to n minus 1 because Zn by norm Zn is Yn. Yn is scalar terms of Zn and Zn is orthogonal. Zn is orthogonal with yk and Yn is scalar times of Zn. Therefore, Yn also will be orthogonal with yk. Okay. Now we showed that y1 up to yn minus 1 are orthogonal, right? And we have to show that the linear span of xn's is the linear span of y's, right? Linear span of x1 up to xn is equal to the linear span of y1 up to yn. Okay. Let us start. Let us take an element from here. Let x belong to linear span of x1 up to xn. Okay, means what? X is equal to some c1 x1 up to cn minus 1 xn minus 1 plus cn xn. Okay, there exists scalars c1 up to cn belonging to the field. Okay. X is a linear span of these n vectors means X is a linear combination of these n vectors. Means there exists scalar C1, C2 up to Cn such that this linear combination is equal to X. Okay, and these are scalars. Now you look up to this, right? This is the linear span of x1 up to xn minus 1. So this can be written as some d1 x y1 plus dn minus 1 yn minus 1. Why? This is a linear span of x1 up to xn minus 1. So this can be written as this one, right? This linear combination of the vectors x1 up to xn minus 1 can be written as linear combination of the vectors y1 up to yn minus 1 because of the induction hypothesis, right? Because of this, you can write linear span of linear combination of x1 up to xn minus 1 is linear combination of y1 up to yn minus 1 because of this induction hypothesis. This is induction hypothesis. This is the hypothesis. Okay. So because of that, yeah, this is this plus cn. What is xn? Can you write xn in terms of yn? Can you write xn in terms of yn? Now this is Zn. Yeah. Now Zn is divided by norm Zn. So xn by norm Zn comes, all this comes. Okay. This whole thing is divided by norm Zn. So xn by norm Zn comes here. And you take all this to the other side, xn by norm Zn comes. And so this vector is Zn, right? It can be written in terms of this. So, Zn is what? This one. Xn minus sigma xn yi. Zn is this. Okay, let us take this. Zn is right. In fact, I am forming Zn by norm Zn. Okay. Zn is what? Xn minus sigma xn comma yi equal to 1 to n minus 1. Okay, this is Zn, and you are dividing this by its norm. Right? Yeah. To get yn, you are dividing Zn by norm Zn. Okay. So yeah. Now what happens? You don't need bracket here. Right? So that becomes what? So from here, you can write yn equal to zn by norm zn, and this is xn by norm zn minus sigma. This is a scalar xn by I by norm zn into yi, where I equal to 1 to n. Okay, right? So yn is and you can, these are what, this is a linear combination up to n minus 1. This is a linear combination of y1 up to yn minus 1. This can be taken to the other left, this side. So your xn becomes, xn by zn, norm zn becomes a linear combination of y1 up to yn. So xn becomes a linear combination of y1 up to yn. Okay, so this implies that xn by norm zn is equal to yn plus sigma xn comma yi by norm zn into yi equal to 1 to n minus 1. I have taken these things to the other side. So it is yn plus sigma this thing, yn plus sigma this. Okay, and this is a linear combination of y1 up to yn minus 1, y1 up to yn. Okay, so this is a linear combination. This is a linear combination of y1 to yn. Okay, and this is what you can take norm zn to this side. So xn is norm zn into this scalar. Okay, means this is a linear combination. Is a linear combination of y1 up to yn. Okay, therefore, if you club in the induction hypothesis that these two linear spans are same, okay, it gives you that xn is also a linear, right? And if these vectors are in the linear span of y1 up to yn minus 1, these are also in the linear span of y1 up to yn. Okay, if you increase one more vector, there's no harm. This linear combination will also be the linear combination of the vectors y1 up to yn. Okay, so that's how these also will be in the linear span of y1 up to yn. Okay, so if you club this with this, you get that x1 up to xn will be in the linear combination of this, right? If you give a number for this, if you give a number for this, star 2, so star 2 implies that x1 up to xn belong to linear span of y1 up to yn. Okay, right? Therefore, linear span of x1 up to xn is contained in the linear span of this, right? And if you take the other way around, if you take a linear span of these vectors, yi's, can we show that they are in the linear span of this? Yeah. So if you take a linear combination of y1 up to yn, what do you have? You will take this kind of a vector into yn, into xn, sorry. Okay. Right. If you take a linear combination of y1 up to yn, it will be of the form d1 y1 plus up to dn minus 1 yn minus 1 plus cn plus some dn yn comes here. By induction hypothesis, this up to this yn minus 1 first term, it can be written as this one. Okay, and the term yn is this scalar multiple of yn, right? Can it be written as in terms of xn? And yn is a scalar times of zn, and zn is what? Zn, right? Zn is this one. So yi is up to I equal to 1 to n minus 1. These are in the linear span of y1 up to yn minus 1. These are the linear span of x1 up to xn minus 1 by induction hypothesis. These are the linear span of x1 up to xn minus 1. And therefore, this is in the linear span of x1 up to xn. Okay. So yn will be in the linear span of x1 up to xn. Okay. That's how a scalar times of yn will also be in the linear span of these. So if you club the induction hypothesis, this from here you will get that linear combination of yns will be in the linear combination of x's. Okay. You have to, I think you can write it yourself. Can you do it yourself? Hello. So let yeah, or consider y1, no, consider d1y1 plus dn minus 1 yn minus 1 plus dn yn. Okay, and this is equal to up to this one. This can be written as some c1y1, some c1x1, some c1x1 up to cn minus 1 xn minus 1. This is y. Okay, by induction hypothesis, the first this first n minus 1 terms, they form the linear combination of y1 up to yn minus 1. This can be written as a linear combination of x1 up to xn minus 1 plus what is yn? What is yn? Let us bring. Our yn is norm Zn minus this one, Zn by norm Zn. This is Zn by norm Zn. What is Zn? Zn is xn minus sigma xn comma yi where I equal to 1 to n minus 1. Okay, by definition, this is how Zn. Now, this involves y1 up to yn minus 1. Right? These are linear by induction hypothesis. These are linear. Right? This linear combination is a linear combination of x1 up to xn minus 1. So this is xn minus some k1 x1 minus plus and so on plus kn minus 1 xn minus 1 by induction hypothesis, by induction hypothesis. Right? By this induction hypothesis, right? This is a term, this is a linear combination of y1 up to yn minus 1. So this can be written as a linear combination of x1 up to xn minus 1. And this is a linear combination of xn, x1 up to xn minus xn. Okay. So Zn is a linear combination of x1 up to xn. And this is a scalar. Scalar times of that will also be a linear combination of x1 up to xn. Okay. So if you plug these two, therefore, right, this thing, sigma, therefore sigma di yi I equal to 1 to n is a linear combination, of x1 up to xn. Okay, Zn is a linear combination of this x1 up to xn, and right, and therefore, and this is a linear combination of x1 up to xn minus 1. And Zn is a linear combination of x1 up to xn. Therefore, this whole thing will be a linear combination of x1 up to xn. Okay. Therefore, linear span of y1 up to yn is contained in linear span of x1 up to xn. Okay. So I have right. Previously, we proved that what we proved. This is linear span of xn's is contained in linear span of yn's. How about this is linear span of yn's is contained in linear span of xn's. Okay. Right. This is linear span of x1 up to xn is contained in linear span of y1 up to yn. Means these two linear spans are same. Therefore, you have equality here. If you plug this one, you call this 3, right, by 3. Okay. By 3 you have equality here. That is the conclusion of the theorem, right? we want linear span of x1 up to xn is linear span of y1 up to yn. Okay, and also that these yns are orthonormal. Okay, that's how we construct it. We showed that right, Zn comma yk is orthogonal. From that we showed that yn comma yk is orthogonal. Okay, so the vectors y1 up to yn minus 1 and yn, these become orthogonal. And how about yn? These are up, right? y1 up to yn or yn minus 1 are orthonormal. How about yn? Is it of one unit 1? Is it of length unit 1? Is it a unit vector? Right? If you take the norm of this, because of this, if you take the norm of this, it will be 1. Okay. Right? Norm Zn. Norm, right? What is yn? Yeah, norm yn is norm Zn by norm Zn. That is 1. Okay. Norm of yn is equal to norm yn is equal to norm zn by norm zn. You're dividing this vector by its length. So this is norm z. So what happened? Right? Yeah, I should not write here. So this is norm zn by norm zn. That is gone. Okay. So yn is of length 1 and it is orthogonal with y1 up to yn minus 1. Right? It is orthogonal. Yeah. It is orthogonal with the other y case. Okay. So this is what is known as the Gram-Schmidt orthonormalization. If you are given n linearly independent vectors, you can construct n linearly independent vectors which are orthogonal and orthonormal. Okay, right? In fact, these are right. Every set of orthogonal vectors is orthonormal. Of course, if zero element is not there, you should not have zero element in the orthogonal vectors. Okay, then orthogonal vectors will be linearly independent. Okay, this point should be kept in mind. Okay, and the next theorem, rather proposition, which I missed before this Gram-Schmidt orthonormalization is this. Okay, it is this proposition. It is proposition 12.5.3. 12.5.3. Okay, let X be an inner product space. Let X be an inner product space. Right. An orthonormal set in A and orthonormal set A in X is complete. If and only if for any X in X, for any X in X, for any X in X, such that X is orthogonal to Y for all Y in A implies X equal to 0 vector. Okay. Okay. We must have. This can be replaced by we must have. We must have. Yeah. Okay. In an inner product space.
What is this, sir?
Yeah, this is 12.5.3. Page number 191. 12.5.3. Let X be an inner product space. An orthonormal set A in capital X is complete if and only if this is true. Okay. See, you are inside an inner product space and yeah, you are taking an orthonormal set capital A. You are taking elements here and these are mutually orthogonal and they are orthonormal also. They are all unit vectors. Okay. Then the set is complete provided this condition is satisfied. Okay. What is complete? When you say an orthonormal set is complete, if this is not contained in a larger set, if this is not contained in any other larger orthonormal set, then we say this set capital A is complete. Okay. So if that is true, then we can obtain this. See how. This part. Okay. Proof. I just outline the proof. Yeah. So let orthonormal set A contained in X be complete. I mean, assume this one. I want to derive this. Okay. So this property, you take X varying in capital A. Let the X be in this set, and then no. X is coming from any throughout X. Small x can vary in X, so it can be outside also. Okay, X can come from anywhere. It can come from A also. These are X values. Okay, X1, X2 like that. And then Y is coming from, these are Y also, Y1, Y2. These are coming from capital A. if X values come from anywhere from capital X, they can be in capital A or in complement. Those are X values. And Y values come from capital A alone. And in that case, X and Y must be orthogonal. And yeah, if your small x is such that this holds, then this property must give us X is 0 vector. Okay, so let us assume this. Let us start with negation. Let X be non-zero such that this is true. Let X be satisfying this, but X is non-zero. So let us start with negation. Okay, yeah. Let X belong to capital X be such that X is orthogonal to Y for all Y belong to capital A. You assume this. You assume from here to here, but you assume the conclusion is false. Okay, so let, if possible, X be not 0 vector. Okay, he says the completeness of capital A and this one together give this. Okay, so let us assume that capital A is complete, and then let us assume this also, and let us derive this. But if it is okay, right, let us start with negation of this. So I am starting with the negation. So X is non-zero, and now, because your X is orthogonal to Y. Now consider this. Consider capital A union, right? Orthonormal. For complete sets, you have define orthogonal. Yeah. Okay. Orthonormality define. It doesn't matter. For completeness, orthogonality and orthonormality both are equivalent. Okay. Now, yeah. Okay. Then you consider this A union X by norm X. You are assuming your X is non-zero, so norm X is positive. You are assuming your X is non-zero vector, so norm X is positive number. X divide X by norm X. So this is a unit vector, and because of this property, this will be orthonormal. Right now, this is orthonormal. Because if you take the inner product of this with an element in A, so X by norm X, inner product Y is equal to, this scalar can be taken out, norm X, inner product X comma Y, right? You let small y, where your capital A, take its inner product with X by norm X. So this 1 by norm X is scalar, take it out. So inner product X comma Y. And because X is orthogonal to Y for every Y in A, right? So because of this, this is 0. This is 1 by norm X into 0. So this is 0. So this gives that this set is orthogonal with each and every vector in capital A, and this is also orthonormal. Therefore, capital A union capital X by norm X is orthonormal. Okay. And also, because you are assuming that, so can your X be in A? Can your X be in A? What happens if your X is in A? What happens if where is X, right? What happens if your X is in A? Can your X be in A? See, you take this property. If X belongs to A, then what happens? In place of Y, you can take X. So X inner product X. This will be norm X square. And X, if small x is in capital A, in place of Y, you can take small x. So X is perpendicular to Y. X is orthogonal to Y. So this is 0. Okay. If small x belongs to capital A, in place of Y, you can take small x. So X is orthogonal to small x. Small x is orthogonal to small x means this is 0. Okay, this is norm X. This means what? This implies X is 0. Okay. So if you take X to be in capital A, your X turns out to be 0 vector, but your X is non-zero. Therefore, this is a contradiction. Okay. Okay, this is a contradiction. So therefore, your x is not equal to 0 vector. Your x is not in A. Your x is not in A. Okay, so your x does not belong to A. Now, therefore, this also will not be in capital A. X by norm x will also be in capital A, because multiplying x by a scalar does not change this property, right? If had you taken x by norm x would have come here, right? If you would have taken x by norm x here, norm x goes out, x product x comma x remains. So this becomes norm x. It is equal to 0. So you have x equal to 0. So still, right? And so this gives, right? If you give this 5, yeah. So the 5 implies that x by norm x does not belong to capital A. Okay, this and 5. This property and this give that x by norm x is not in capital A. So you could get an element which is not in capital A, and this union is orthonormal. So capital A is contained in larger orthonormal set. Therefore, capital A is properly contained in A union x by norm x. Okay, which is orthonormal, and this violates that your capital A is complete. What kind of a set is capital A? Your capital A is complete. Capital A is complete. It cannot be contained in any larger orthonormal set. It cannot be contained in any larger orthonormal set. This is properly contained in this orthonormal set, which is larger than capital A. This contradicts the maximality of capital A. Therefore, right? Because capital A is complete, it is maximal. So this cannot happen. This all happened because we took that our x is 0. Right? Or x is non-zero. We assumed our x is non-zero. It all happened due to this. Okay. So x has to be the 0 vector. Okay. Therefore, x is 0 vector. Okay. That is right. One implication. Necessary part. The sufficiency part. Let us look at the sufficiency part. So let approaching time. Let x belonging to x be such that x is perpendicular to y for all y belonging to capital A, implying x is equal to 0 vector. Okay, let us assume this. Let us prove that. Let capital A be an orthonormal set. Okay, consider let capital A be orthonormal. Capital A be orthonormal. You have to show that it is maximal. Okay, to show that capital A is complete. Suppose it is not. To start with negation. Let A be not complete. Means what? Means what? There exists an orthonormal set, an orthonormal set, capital A1 contained in X, such that A is properly contained in A1. Okay. What is negation of this? What is what do we mean by completeness? A is not contained in any larger orthonormal set. What is its negation? It is contained. It is properly contained in a larger orthonormal set. Okay, we are starting with negation. What does this mean? What does this mean? There exists an element in this which is not in this. So there exists a y belonging to A1 minus singleton A. Because it is proper, there will be an element here which is not here. Okay, and A1 is orthonormal. A1 is orthonormal. So it will be orthonormal with the elements in capital A also. Right? So this implies that y intersection x is equal to 0 for all x belonging to capital A. Okay. A1 is orthonormal. Y is in capital A1. So it will be, and A1 contains A. So you will have this for all x in A, y will be orthogonal. Okay. So, but hypothesis says that if an element y is like this for all x in capital A, then that x, then yeah. So I have interchanged, I think. Here x Yeah. Here X is varying, here Y is varying. Here Y is varying, here X is varying. So I have to interchange. Okay. So this gives X equal to 0. So this gives Y equal to 0. Okay. Here Y is varying. Here X is varying. But the property is same. I have interchanged. In place of X and Y, I have got Y and X. So you get a conclusion is X equal to 0. Here conclusion will be Y equal to 0. So I started with a Y in capital A1 and I got Y is 0 element. Can this Y be 0 element? Can this Y be 0 element? If Y is 0 element, what is its norm? Norm Y will be how much? 0. But it is orthonormal. What is its norm? Orthonormality gives you what? Norm Y is equal to 1. Can 1 be 0? No. This is a contradiction. Okay? Right? Orthonormality gives norm Y is 1. Y is in A1. A1 is orthonormal. Okay? Norm Y will be 1. But we have got norm Y is 0 vector. So its norm is 0. So this is 1, this is 0. They are not equal. Therefore, our assumption is wrong. Therefore, Y A not complete is wrong. Therefore, A has to be complete. Okay? So that's how we prove the sufficiency part. Okay? Therefore, you have this. So, right? If you have an orthonormal set, completeness is equivalent to this property. Okay? Right? So, that's how we prove this proposition. Right? You have to practice very well. Okay? And as days are nearing your exams, the quantum of mathematics you are learning is becoming huge and huge. And you will be getting confused. So I don't do much. I thought I have to, right? I don't know, like what else can I do? Let's say I plan open mapping theorem and closed graph theorem. Briefly, I want to do them, and maybe on complements I want to do a little and then stop. Okay, will it be okay?
Okay, right? Sir.
Because if I do Hahn-Banach theorem, you people may get confused. It is very involved. Hahn-Banach theorem is very involved. So I may talk on its one of a couple of applications. Okay, and I don't want to do Hahn-Banach theorem because it is quite involved. You people may get confused, and you cannot see. The point is, if you mug up the things and if you commit mistakes, while presenting, your logic will be wrong. Your mathematics will be wrong. You try to understand the notation and the concept and try to be perfect. Whatever you write, try to write them perfectly, like the way I write. So if you write like that, then you get marks. And if you go for wrong notations and then wrong logics, and then you don't get marks. Okay, so you please be sure. And the point is, you have to practice. That is the only way. Okay, you understand definitions, and then you be careful with notation. Right? You cannot write, if you want to write A is in capital A, you cannot write capital A like this. Okay, right? So you should be careful with notations. Some people, so many blunder mistakes people commit because they are so careless. Mathematics is not like that. They write, if F is a mapping from X to Y, they write F takes Xn to something like this. Like, no, like you should be very careful with notations. Okay, so please practice these, and this part maybe I will do for, say we have 5 more lectures, 5 more sessions. Maybe in 3 more sessions, I will discuss complements in one session, and closed graph theorem and open mapping theorem. Closed graph theorem and open mapping theorem in one session each, and complements, orthogonal complements in one session. Okay, so 2 more remain. For those 2 more sessions, we'll discuss question paper. Okay, we'll discuss how to write question paper. We'll take one or two previous question papers, and we'll see how we can answer them. Okay, that's a kind of discussion, right? A kind of model examination. Okay, so I think that will enable you to write exam in a good fashion. Okay, that's what I am planning. Will it be okay? Any suggestion?
Yes,
any suggestion?
You said you'll do some problems.
Yes.
You'll do some problems.
Some problems?
Oh.
Problems on what?
So on this,
based on this theory, the inner product theory.
Yes, sir. Yes, sir. You said you will do it.
Yeah. I said because I'm afraid you may get confused. So that's what I am doubting. Okay. So what we do is maybe because we have completed Gram-Schmidt orthonormalization. Okay. And then we'll complete. See this closure graph theorem and open mapping theorem. We'll complete them in 2 sessions, and then we'll come back and we'll discuss some old questions from old papers. Okay. Will it be okay? I'll be solving some old questions from previous papers, and I cannot solve each and every question in that paper. You don't fail me in those when I answer those question papers. I'll get pass marks. Okay, right? That is our agreement. Okay, so for 2 more sessions, I will do closure graph theorem and open mapping theorem, and after that, 3 sessions will remain. In that, we'll discuss some old papers. Will it be okay?
Okay, sir.
Okay, right. I'll stop here. Any questions? Any questions? Okay, goodbye. Thank you.